Hello. The last exercise has thrown a bit of a spanner in the works with everything that we have been looking at in this series of exercises. In all of these exercises, we have been writing programs to calculate the sample mean by using the expression shown at the top of this slide. Furthermore, we have seen that as we increase n, which is plotted on the x-axis of the graph, and thus increase the number of random variables that the sample mean is calculated from, we see that the sample mean, which is shown on the y-axis of the graph, behaves something like what is shown here. We have seen that this happens because the sample mean is an accurate estimator for the expectation of the distribution. Furthermore, the more random variables the sample mean is computed from, the more precise an estimator for the mean it is. Any sample mean computed from a large number of random variables will thus give a value that is close to the expectation of the distribution. When you plotted your graph like this one for the random variable that was introduced in the previous exercises, however, you will have observed a behavior that was perhaps something like this. This does not appear to be getting progressively closer and closer to some fixed value. You thus might legitimately ask yourself, what the hell is going on? We can understand what is going on here if we derive an expression for the expectation of the random variable that is being sampled. The random variable here is equal to 2 raised to the power of a random variable called t. T is itself a geometric random variable and thus has the probability mass function that is shown here. Furthermore, the parameter p of this distribution is equal to 0.5. We can calculate the expectation for the random variable capital Y in the usual way. Y is just a function of a random variable, so we can use our familiar expression for the expectation of a function of a discrete random variable as is written here. Inserting the expression for the probability mass function for our geometric random variable into this then gives the following. Lastly, by recording that p equals 0.5, we can rewrite 1 minus p to the n minus 1 times p as a half raised to the power n. The 2 to the n in the numerator here cancels with the 2 to the n in the denominator to give 1. We are thus left with the following infinite sum. If we add 1 to itself an infinite number of times, however, we get infinity. The expectation of this random variable is thus undefined, which brings me to the point of this little exercise. Some of the moments of random variables are not defined. So before calculating the sample mean and saying that this is a meaningful quantity, you need to check that the expectation exists for the distribution you are sampling. Thanks for your attention, and well done with the exercises this week.